Good morning. We're going to begin our discussion on Chapter 3. Before we get into Chapter 3, let's recall what we have done so far. Essentially, we have derived in general the expressions for the electric field E of R and also an expression for the potential phi of R. So if I have an arbitrary charge distribution and we are interested in the field or potential at point P, which is at a distance R from the origin, then I can divide this volume into small segments and I can go to each segment and treat it as a point charge. So I go to each segment and treat it as a point charge. So the total charge in this region is rho of r prime, where r prime is the vector from the origin to that particular point, times the volume d cube r prime. And this distance from that cell to P is r prime. So when we are summing up the contributions of each of these cells, we are essentially integrating over this. So we would have E of R to be something like K rho at R prime d cube R prime by R minus R prime cube times R minus R prime, right? So here this is the magnitude and this is just the vector r minus r prime because the direction is along r minus of the electric field is along r minus r prime. So we're including the direction, so that's why we have a cube here instead of a square. This is not a magnitude, this is within the square brackets. So similarly, we can write an expression for phi as well, k times rho of r prime d cube r prime. Now you don't have to worry about the direction, so we just simply have r minus r prime, right? So these are the expressions for electric field and potential at a specific point. Then we also saw that we could express E as minus grad phi. Using Stokes' law, we have seen that curl of E is equal to 0. You can think about this in terms of an infinite sheet of charge using the Gaussian pillbox. If you go around the loop, we have seen that curl of E becomes 0 due to Stokes' theorem. Similarly, from the fundamental definition of divergence, the fundamental definition of divergence is the volume integral of divergence of E over volume dV is equal to the surface integral of E dot dA. So from this fundamental definition, we used Gauss's law, right? So this is equal to Q by epsilon naught. The charge is, this is the enclosed charge. And then we can write, comparing this integrand to that, we can write that gradient, divergence of E is equal to rho by epsilon naught. Because this is a volume integral, so if I divide this charge by volume, I get the charge density here. So if the charge distribution has certain inherent symmetry, then these integrals are easy to perform, somewhat easy. Still not straightforward. You may have to choose a curvilinear coordinate system like how we have done in case of a sphere. Similarly, in case of a cylinder, you could use cylindrical coordinate system to evaluate these integrals and find electric field and potential. Ultimately, what we are trying to study is if I have a given charge distribution here, and if I bring a test charge Q here, what is the impetus that this test charge is going to feel? We know that force felt by this charge is QE, so its motion would depend upon this, and so we are looking at finding this electric field, and these are the ways, different ways to find that electric field. So in the last chapter, we have seen how we could use Coulomb's law, for example, directly this to get the electric field itself. In some cases, we saw how we could use potential instead to get the electric field. And in some other cases, like the infinite sheet or even a point charge, we used Gauss's law to get the electric field. But this is not necessarily very similar for all situations. So we want to develop a general way to solve these, to solve for electric field and potential. So ultimately, we want to know what the electric field and potential are. So to this end, what we could do is we could take this and substitute in the Gauss's law, which we have done also in chapter 2. So we know that the divergence of E is equal to rho by epsilon naught, but we know that E you can express as grad phi. So then I can write divergence of grad phi is equal to rho by epsilon naught, or the divergence of this grad gives me a Laplacian of phi is equal to minus rho by epsilon naught. We call this the Poisson's equation. So if we can develop general ways to solve this Poisson's equation, then we can solve for phi, and we can get electric field, and then we can get the force, so on and so forth. So a general way to approach this electrostatic problems is through Poisson's equation. But we can look at one special case of Poisson's equation. For example, if the charge density is 0 in a given volume. So I have a volume of space. So this is the volume of space that I have, and there is no charge here. If there is no charge, then in that volume V, I have del square to be of phi to be equal to 0, and this is the Laplace's equation. So first we are going to study Laplace's equation and slowly get into Poisson's equation, because we will look at the solutions and how to use the solutions for Laplace's equations to easily find solutions to Poisson's equation, for example. And we will also develop other methods using this. So while solving Poisson's equation, another thing that you need to bear in mind is boundary conditions. We briefly discussed these boundary conditions in the previous lectures. For example, if I have a spherical shell of charge, again, I'm drawing the cross section. So this is the spherical shell. So inside the spherical shell, E is equal to 0. Outside the spherical shell, E is not equal to 0. So if we want to define the electric field of R in a general way, then we have to adhere to the boundary condition. That is, if I'm going from inside the sphere to outside the sphere, there is this, I have to specify what the electric field is at the boundary in some way. Because at the boundary, is E equal to 0 or E is not equal to 0? How do you determine that, right? So that boundary conditions are important for solving these equations. So first, let's look at the solutions to Laplace's equations. The solutions to Laplace's equation, del square phi is equal to 0. This is in a given volume. So we're looking at a given volume of planar, and del square phi is equal to 0. So the solutions to this are called harmonics. So we're going to learn a few things about harmonics so that we can use these properties of harmonics to solve Poisson's equation ultimately. So if phi is a solution to this, that means phi is a scalar function, in general phi of r is a solution to this equation, and let's say even psi of r, these are two solutions, let's say, right, that satisfy del square phi is equal to 0 and del square psi is equal to 0. Then by the nature of this del square operator, you can see that if I had, instead of phi of r, if I had c times phi of r, where c is a constant, then I can see that del square of c phi of r is equal to c is just a constant, so you can pull it out. You can write it as c times del square phi, which is still 0. So c phi of r is also, if phi of r is a solution to the Laplace's equation, then constant times phi of r is also a solution. Similarly, if phi and psi are both solutions to the Laplace equation like this, then if I have phi of r plus psi of r, then this is also a solution, because if I have del square phi plus psi, that is simply del square phi plus del square psi, which is 0 plus 0, which is equal to 0. Right? So if phi and psi are harmonic, phi plus psi is harmonic, and c phi is harmonic. And you can see other things, phi minus psi will also be harmonic, or some linear combination of these could also be made harmonic. So now let's look at some examples of harmonic functions. Like I said, we're trying to understand the Laplace's equation. The solutions to Laplace's equations are harmonics. Our ultimate goal is to solve Poisson's equations, because we want to get the potential and then get the electric field and then know what is the force on a test charge from any charge distribution. So that's our goal. So the first type of harmonics are homogeneous polynomials. So polynomials can be of different degrees, right? So homogeneous polynomials. So they can have a degree of 0. That means it's just a constant. So if I have constant c, then you know that del square c is simply 0, because c is constant. Or you could have degree 1, which is something like x or y, right? Or in general, ax plus by. The del square of these degree 1 polynomials, for example, any ax plus by, would also be 0, right? Then you could have degree 2 that is quadratic. So these are linear polynomials. Then degree 2, then these would be quadratic, right? So this would be something like x squared, y squared, xy, x squared minus y squared, so on and so forth. And you can see that the del square for x squared should also be 0, right? Sorry, del square for x squared minus, sorry, here x squared and y squared themselves are not the solutions. X squared minus y squared or xy, these would be the solutions, because if you were to do del square of x squared, then that would give you, simply dou square by dou x square of x squared, which is dou by dou x of 2x, or that is 2, so it's not 0. But if you have del square of x squared minus y squared, you would get 2 minus 2, which gives you 0. Similarly, del square of xy would also give you 0, because dou by dou x of y is 0. Right? And similarly, dou by dou y of x would also be 0. So in general, any quadratic solution to the Laplace equation, you can simply write it as a times x squared minus y squared times b plus xy. So this would be a general quadratic solution to the Laplace's equation, right? So these homogeneous polynomials are one type of harmonic functions. So either constant or functions like this, or functions like this in general, for quadratic functions like this would be solutions to the Laplace equation. So another type of solutions to the Laplace equation are functions with radial symmetry. So if you look at something like r is equal to square root of x squared plus y squared, right? And you take a function phi of r is ln r, then this is a harmonic. in spherical polar coordinates, you can write the r component of del square would be something like 1 over r. So for the phi, for the function phi, which is purely dependent on r, this would be r times dou phi by dou r. This would be the Laplacian operator in spherical polar coordinates. So if you were to do this, then you would have 1 over r dou by dou r times dou by dou r of ln r. So that would give you 1 over r dou by dou r times dou by dou r of 1 over ln r is 1 over r. So these r's cancel out, and dou by dou r of 1 is 0. So the Laplacian is 0. So the thing to consider here is in spherical polar coordinates, del square would not just be simply dou square by dou r square, because r, theta, phi are not independent like x, y, and z. So the del square is not simply dou square by dou r square, but the del square in spherical polar coordinates is something like this. And then there is another type of harmonic functions which are exponential. And in terms of exponential, you could have exponentially growing functions or exponentially decaying functions, right? So for example, something like e to the power mx, right, times sine my, right, or e to the power mx times cosine my. These would also be a harmonic function. So then, in general, we have harmonic functions. We have three types. One is polynomials, right? These polynomials, homogeneous polynomials, these include constants and linear functions like x, y, or in general ax plus by, and then quadratic, which are in general a times x squared minus y squared plus bxy. And then we have another type of functions with radial symmetry. So radial symmetry is one of the examples is ln r. Phi of r is equal to ln r. And similarly, we have exponential, right? So that is these functions. So these are different types of harmonics. So now let's talk about average of a function, of a scalar function over a sphere. So the average of a scalar function, so we have a scalar function phi of r, right? And we would like to find the average of this over a sphere. So that means I'm situating myself at some point P, and I am extending to a radius r, and then I'm drawing a sphere around this P. And I would like to find out what is the average of this phi over the surface of this volume. So over the surface of this volume, over this sphere. That means we would like to know what is the average of phi. For example, if this were an orange, we would like to know what this phi value average is on the peel, right? So if you want to do that, what we could do is, we could go to each, we can divide this surface into tiny segments, right? And let's say each segment has roughly an area dA. Then I can go to each segment with an area dAi and take the value of phi at that position. So at phi of Ri or di, so phi I at Ri dAi. So I'm going to the first cell and I'm taking this value. And similarly, I can take the value in the second cell and add them up. So I would have phi I dAi. I is summed over. So this would be something like phi 1 dA1 plus phi 2 dA2 plus phi 3 dA3, so on and so forth. What we are trying to do is we are trying to see how an average looks like, average of a scalar function over a sphere, the surface of a sphere looks like. So then if I divide this by the total area, right, then I can write this as phi I, right, dAI. This area is something like the total number times dAI, right? So if you were to choose all these of the same area, small tiny pieces with all having the same area, right? Then this n times dA, you are dividing the total area into n parts. So each part dA is simply a by n, right? So then this would give you phi I over n, and this phi I is sigma I. Remember that this is summed over, so because we are repeating the index. But here, if all the dAs are same, then I can write this sigma I phi I dAI. If all dAis are same, then I can write it as dA times sigma I phi I, right? I'm pulling the dA out. So that dA can cancel here and I get sigma I phi I over n. So I am getting basically by from here, I'm getting the total average of the function, or I can write the average of a function phi average um, over some volume, or surface of a volume of a sphere or a volume in general, could be written as sigma I, right, phi I dA by the total area A. That's what we had done here, right? So then I can reduce this to almost zero. This dA, I can almost send it to zero and then convert this to an integral, right? So I'm integrating over the surface. So that's the surface integral. I'm taking the phi at each point on the surface and multiplying it with dA and dividing it by the total area. So this would be my average. So this would be the average of a function over a sphere S, over the surface of a sphere S. Now, using this definition, let's look at something called the mean value theorem for harmonic functions. So it's mean value theorem or mean value property of harmonic functions. Once again, we are studying harmonic functions, which are solutions to the Laplace equation, because we ultimately want to solve Poisson's equation. So we're trying to prove certain things here with harmonic functions, so we can take them and use them later. So now that we know what the average of a function is, the special property of harmonic functions is, if I want to know the value of a harmonic function at a point R, I can draw a sphere of radius r around it, drawing a sphere of radius r around it, and I'm taking the average of phi on this surface. So then that average, that phi average, we can write it as integral of phi of r prime d cube or d dA, right, like this, divided by the total area. So the mean value theorem posits that the phi at the center of the sphere, phi of r, is equal to this average over the sphere. This average over the sphere. That's a property of harmonic functions. That is, again, to rephrase it, because it's very important to understand this, what we're saying is, if I want to know the value of phi of r, and phi of r is a solution to del square phi is equal to 0, we call such solutions as harmonics, and if I want to know that phi at one specific value, I'm going out to a radius r and drawing a sphere, and the average of the function phi of r prime on the sphere, that's the average, right? The average of that function is equal to, over that sphere, is equal to the value at the center. So to prove this, let's start the proof for this mean value. We're going to prove the mean value property. That is, again, to write it, phi of r. So phi of r, just give me a minute here, is equal to integral over a surface S, right? Phi of r prime dA prime divided by A. So we are going to prove this. This is the statement of the mean value theorem. To do that, first thing we start with is we know that del square phi is equal to 0, which means we know that the divergence of gradient phi is equal to 0. Now let's integrate this over a volume V, right? So I'm going to integrate this over a volume V, del dot grad phi over a volume V. I know that I can convert this using the fundamental definition of divergence. The fundamental definition of divergence is divergence of a function j over a volume V is equal to the surface integral of j dot dA. So if I convert it into that surface integral, then this would be surface integral of grad phi dot dA over the surface S. So what we are saying is, if I have a region of a volume of space, so I have this volume of space, and within this volume, this is a volume. So within this blob, within this volume, del square phi is equal to 0 within V. And the surface integral is over the surface bounding this volume V, this blob. If you just take the top layer, peel off the top layer like you would peel an orange, so that over that surface, this grad phi dot dA would be equal to this. But we know that this itself is 0, right? So then this integral should also be 0 because the integrand itself is 0, right? Then we know that the surface integral of grad phi dot dA is equal to 0. Now let's take the simple case of a sphere. If I take a sphere and if I take some portion here, right, the area vector here is pointing along R, right? It's perpendicular. It's perpendicular. If I take here, it's pointing up, right? So if I take it here, it's pointing down. So it's perpendicular to the surface along R direction. So the area vector itself would be along one particular direction. So if I say that this dA in general is along some direction n times dA, then I can rewrite this as the surface integral of grad phi dot this unit vector n times dA is equal to 0. Now take the example of a sphere. So if you're looking along the R direction, this particular direction, then essentially if you're dotting it with that direction, you would get only that part of the gradient. So for example, if this n were R, then grad phi dot R would give you the R component of that grad phi. So then I can rewrite this as surface integral of grad phi along n dA is equal to 0. So the grad phi along this direction n in general is dou phi by dou n times dA, right? And this is equal to 0. Now let's take this one. So we have integral, the surface integral of dou phi by dou n. Again, we're trying to prove the mean value theorem here. And what I'm trying to look at is connect the average to the value of the function at the center. And that's what we are trying to prove. So dou phi by dou n times dA is equal to 0, right? So if I divide it by area and multiply it by area, right, then I get essentially integral of dou phi by dou n dA by A, right, is equal to 0. This dA by A itself is like a number. It's just a number because I have the total volume A, and I have I'm dividing this total volume by n, so I'm getting n dAs. So right, so dA by A itself is like 1 over n. We took out the vector part of dA. We took out the vector part of dA through this n vector, so that is appearing as dou by dou n here. So this itself is independent. It doesn't have any dependence, 1 over n dependence. So I can then write it as dou by dou n of integral phi dA by A is equal to 0. But we saw that this is nothing but the average of phi over the volume, over the surface bounding the volume. Surface bounding volume V. Right? That's what we have seen as the definition of the average, right? Or here rather. So then I can see that the dou by dou n of this average is equal to 0, right? So the average itself is not changing radially. So what does this mean physically? Physically, it means that I have a volume. So let's say I have this volume, right? This is a volume. Imagine this huge blob, and inside this blob, let's say the equation del square phi is equal to 0 inside this blob. If del square phi is equal to 0, then phi is a harmonic, and what that harmonic means is within this volume, if I were to pick any point, if I pick this point here, let's call it R, right? At this point R, the value of phi of R is simply you extend out into the space by R, you draw out a sphere, you average phi over the sphere, right? So phi of R would be 1 over 4 pi R squared, that's the surface area, integral phi of R prime dA prime. This is the mean value theorem. But what we have just derived shows us that this average itself is not changing, because this dou by dou n of phi average is equal to 0, right? So the average itself is not changing. So that means if I were to shrink this sphere down, if I let R, the capital R, go to almost 0, so I would have something like I have a point R and I'm drawing a very tiny sphere where R is almost going to 0. And if I average it over that tiny sphere, then I should get phi of R, right? And the fact that this average is not changing means if I shrink the sphere from capital R to R going to 0, this average value itself is not changing, right? And that gives rise to the value at the center. Because if I shrink the sphere, if I shrink this R to 0, I'm almost going to just this point, right? So that's how we know that the mean value property is right. That's how we prove the mean value theorem. The mean value theorem, again, says that phi at a point R is equal to the average over 4 pi R squared phi of R prime dA prime. So now, then we are going to go back now that we have learned enough about harmonic functions, we're going to go back to the Laplace's equation. So our ultimate goal is to see del square phi is equal to 0 and find a solution for this. We have seen how these solutions will behave, but we have not yet really discussed how to find a solution directly as such. But before we talk about the solution, there are three things to this. One is the existence of a solution. So a solution should exist to this equation. Then we need to have a unique solution, right? And then we can solve for the specific, what the specific function is, and find it out. So in terms of electrostatics, we want to have a unique solution because the charge distribution will only produce one kind of field, right? So we are trying to get these unique solutions that are pertinent to our problem setup, right? So the first thing we want to show is that we can uniquely find these solutions, and that we can show through what we call as Helmholtz theorem. And to this end, we will use the properties of harmonic functions that we just discussed. So what does this Helmholtz function theorem say? Suppose you have a region of space or plana indicated by a volume V. Within this volume V, suppose you define del dot E as some function f of r in general, and curl of E as a function g of r in general. These are defined in volume V. It is very important to differentiate between volume and surfaces, because we have volume integrals where we are taking an entire potato, breaking it into small chips, and integrating over the entire volume, versus just the surface, that would be just the peel of the potato, right? So it's very important to differentiate between volume and surface here. So we have del dot E and curl E defined in a volume V, and we are given a boundary condition. The boundary condition is we're defining the electric field R as h of r, some function h of r, on surface S bounding volume V. So this is our supposition. Suppose you have del dot E, curl E, and E on the surface of a volume V. In a realistic example, what it would look like is, for example, if you go back to the thin spherical shell, right? We are defining what is del dot E and curl E in the entire volume of this spherical shell, but we are also defining what is the electric field value on the boundary. Recall that I talked about boundary conditions. So when you go from inside to outside, you have a specific field at the boundary which you are defining only on the surface bound by this volume. If you have these things, and if f of r, g of r, and h of r are specified functions, you know what they are, you're specifying them. If they are specified functions, then the Helmholtz theorem says that you can uniquely find a solution to E. You can find a unique solution to E of R over the entire volume, E of R over volume V, right? So this will uniquely determine the electric field. So to restate the Helmholtz theorem, if you are given del dot E and curl E within a volume, and you have a boundary condition that defines the electric field, what the electric field is on the surface, and these things f, g, and h are specified functions, then you have a unique solution to E. So now let's assume that to prove this Helmholtz theorem, we're going to prove this. To prove this, let's assume that there are indeed, the solution is not unique, but let's assume there are two solutions, right? So we're going to prove it sort of like a counterexample. Or a contradiction. So if I have two solutions, let's say E of R and E prime of R, both of these are solutions, then I'm going to define a new function. So we're going to define a new function. Let's call it Z of R, which is the difference between E of R and E prime of R, right? So now if I take the divergence Z of R, the Z is also a vector function, then that would be divergence of E of R minus E prime of R, which is equal to divergence of E of R minus divergence of E prime of R, the two solutions. But because both E and E prime are solutions, and we have del dot E is equal to f of R, we should have del dot E prime also equal to f of R, because that's what we are specifying. We're specifying the divergence to be this. So if it's a solution, it should satisfy that. So both E and E prime, because we're assuming that there are two solutions, they should satisfy this condition. So then you would have essentially f of r minus f of r, right? Then that is equal to 0. So the divergence of z is 0, where z is the difference between these two solutions. So then if divergence of z is equal to 0, then I can look at the curl as well, right? Which is also 0 by the same argument, because E and E prime both are solutions. So both curl of E is G of R, and similarly curl of E prime is also G of R, because they both are solutions. So curl of Z would be 0. That means I should be able to express Z, and the divergence of Z of R is 0, and the curl of Z of R is 0. And in general, we have seen Z of R, we defined it as E of R minus E prime of R, where both E and E prime are solutions. What we are trying to do is we are trying to prove Helmholtz theorem. Helmholtz theorem is stating that if you're given the divergence and the curl of a field and the boundary condition, you can uniquely determine it. So we started with two solutions, we took the difference, and we see that the divergence and curl of the difference is 0. But if the curl of this function is 0, then I should be able to describe the z of r as gradient of some scalar function psi of r, right? Because we showed that curl of a gradient is 0. So if I can write this as gradient of phi, then I can plug this in here. So then I would have del dot um, gradient of phi is equal to 0, or then I have del square psi is equal to 0. So psi should be a harmonic function. But we have seen that the harmonic functions, you could have different types of functions, but for this thing to be, to prove that the solution is unique, we need to prove that z of r is equal to 0. Only then the solution would be unique. If z of r is equal to 0, that is, there is no difference between these two solutions, that is, E is equal to E prime, then we have shown that the electric field is unique. So that's what we want to show, that z is equal to 0 to prove Helmholtz's theorem. But to show that z is equal to 0, we know that z is equal to grad phi. So z would be 0 only if psi of r is a constant. And we do know that psi of r being a constant is a harmonic function, so it could satisfy this. But there are other functions, other harmonic functions that could satisfy this as well. But we can prove that our uniqueness theorem, the Helmholtz theorem, is correct if we can prove that this psi in this case should necessarily be a constant, right? So we can prove that by using the mean value property, right? So now let's assume that there is some volume here, and within this volume we have a psi which satisfies this del square psi is equal to 0, right? And we know that the boundary condition, we know the boundary condition that E of r on the boundary should be equal to h of r. We're given that, the boundary condition, and within the volume del square phi is equal to 0. So if I take one particular point r, and I want to know the psi of r, then from the mean value property I can write this as, if I go around a sphere of radius r, then I can write this as 1 over 4 pi r square psi of r prime dA prime. This is what we have seen as the mean value theorem, right? So from this property, we can say that that this harmonic function psi, whatever it is, it has no local maxima or minima within this volume. So we are saying that the function psi has no local maxima or minima. So how do we prove that? That is very easy to prove. So suppose assume that assume the opposite. Again, we got into proving Helmholtz theorem, but there are sub-proofs here. right? Our ultimate aim is to prove that this particular solution to this equation is a constant. So to prove that, we are invoking the properties of harmonics, but by proving that psi is a constant, we are going to prove that the difference z of r is equal to 0. So don't lose track of that. So if I suppose that there is psi of r that is indeed a local maxima or minima, then on the sphere, if I take psi of r prime, that psi of r prime should always be less than psi of r if psi of r is a local maxima, right? So for example, if psi of r, let's say at the center, let's say psi of r is indeed a local maxima, let's say its value is something like 100, right? So then within its near vicinity on the surface of the sphere within the volume R, at any point, the value should be less than 100. That's the definition of a local maximum. It's the local maximum, right? So on the sphere, anywhere, the value should be less than 100. So if you do 1 by 4 pi r square integral psi of r prime dr prime, this will be less than psi of r. Why? Because if I have, if I assign to each point some value on the sphere and it should be less than 100, so I can go anywhere between 1 to 99, right? And even if I assign 99 to everything on the sphere, the average would still be 99. It would never be greater than 100. If you average numbers that are smaller than whatever is the value here, you're not going to get a number bigger than what is at the center. And this clearly violates the mean value property. So then our supposition that psi of r is a local maxima or a local minima is wrong, because if it is a local maxima or minima, then the mean value theorem is violated. And we know that the mean value theorem is right because we proved it. And so there cannot be a local maxima or minima for psi. And if there are no local maxima or minima, then psi must be a constant, because there are no local maxima or minima, so it should be the same value everywhere within this volume. So del square phi within this volume, the specific solution for this is psi is a constant. And going back, we started with z being the difference between E of r minus E prime of r. And we saw that z is equal to grad psi. And we showed that psi should be a constant from the properties of harmonic functions for this specific case. So then z is equal to 0 because psi is a constant. Therefore, E of r is necessarily equal to E prime of r. That means the solution is unique. So using the properties of harmonic functions, what we have shown is that if I specify del dot E to be a particular function f of r and curl of E to be a specific function g of r, and on the boundary, these are within volume V, right? And on the boundary, I'm specifying a boundary condition on the boundary that this is on the surface S bounding volume V. So if I have all these conditions, then the solution to this E of r is unique. That is what we have shown. So that is, if we have the right boundary conditions, then we can find a unique solution to the electric field. So after having shown this, we will look at things like Green's function and separation of variables to actually find that solution. Like I said, once you have an equation del square psi is equal to 0, right? This itself, the equation itself, doesn't tell you anything about existence of a solution. So first you need to know that there do exist solutions. So, and we have seen several examples that do solve this equation. And then we want to make sure that we can uniquely determine the solution for our problem. And the way to determine that uniquely is by knowing del dot E and curl E. These two things are set by the nature of the charges. Del dot E is equal to rho by epsilon comes from the nature of charge, because a charge is like a faucet that's pumping out water. And similarly, curl of E also comes from that reality. So we're going back to reality. We know that del dot E and curl E, and we given the specific problem. For example, if you have just a point charge, your boundary condition would be the electric field at infinity should be zero. Right, as you go farther and farther away from the charge, your electric field should decrease. So that would be your boundary condition there. But if you instead have, let's say, just a spherical shell, then you need to specify the electric field on that boundary, and that's what this condition is. If you do these, then we know now that we can uniquely determine the solution. Knowing this, now we will try to figure out how to in fact solve these. Thank you.